All right, we're back recording. Going to go over these poster notes with you guys. These are thumbnails. I think you guys should have if not all of these, most of these, right? So let's start with what variables and units are we looking at, right? Yeah, so grading the papers that I've gotten so far, yeah, this looks like a thing that some of you guys gonna have to get used to, right? Remember, there's like some variable, and then you can describe it in some unit. So for example, if you see x equals so many meters, right? Or you guys did centimeters back on Thursday and Friday, right? So x equals some number of meters. So there's going to be a variable, and it's equal to like some number of, and then some units, right? And that's true for like pretty much all the numbers that you guys are going to see in this physics class, right? There's always some unit attached to them, and they're describing some variable. Right? If you see L, this could be capital or lowercase. That could describe a length, right? You could also describe that in centimeters, meters, kilometers. Right? So this could just be an example unit. It could be meters, right? If you see R, I try to use capital R for a fixed radius and lowercase r for a for like a variable radius, although I'm not 100% consistent on that. Right? But that could also be in meters, kilometers, something like that. Right? If you see H or Y, that refers to some height change or vertical displacement. So you could say H equals 1 meter. That could be like the height of a desktop or something. Right? Ooh, T, time could be measured in seconds. So time equals 3 seconds, like that. Right? Sometimes I'll use capital T for time period, and then lowercase t used more often than not in these equations. Right? So lowercase t usually. Right? V, so it comes from the word velocity. Right? So velocity, like how fast, right? But sometimes I'll call it speed, although these are really slightly different things. So speed is just how fast you're going. Velocity is, yeah, how fast you're going, but also there's a direction that's either specified or implied. Okay? So if you look at the speedometer on your car, all that tells you is speed, how fast is the car going. Okay? But if you say going like also like north, right? Okay, well now you've established a direction that makes it a vector. Right? That becomes important. Here, I'll tell you one reason that becomes important. Right? Guys, if you turn the steering wheel, can you feel that? You can feel that, right? If you turn the steering wheel, right? What that means is that there's some kind of force and some kind of acceleration going on, which means that your velocity would not be constant, although your speed could be constant because the speedometer needle could be just pointing to the same number, right? So you can have constant speed, but not constant velocity if you're going around a curve, right? Okay, so that'd be important. But if now let's throw some subscripts on the V, right? I like to use this little subscript not just because I learned it that way back in high school myself, right? So that could be like an initial velocity. Now you guys back in your car and incline lab, you released the car from rest. Therefore, that number was equal to like 0 meters per second, 0 centimeters per second, okay, at the beginning of the interval. Anything that starts from rest. Some textbooks, some instructors use v sub I for initial velocity, so you'll see that too. Okay. If you see the subscript F, that means final velocity. Now, your guys' case, the car and incline lab, that was how fast it was going at the end of the incline. Right? If you guys had those speed gates, right, then that's the number you were getting. Okay? Right, so and the car was probably speeding up uniformly from beginning to end. But if you know the velocity at the beginning of an interval and the end of the interval, and you assume that's either speeding up or slowing down uniformly from beginning to end, there's enough information there where you can solve all kind of stuff, right? Called uniform motion, right? In fact, that goes hand in hand with this. It's called constant acceleration. So those cars were accelerating, right? They were speeding up. Right? You can quantify that in. Well, here, think about where this unit comes from, because right, if there's a change in velocity in some time interval, it's like, well, how fast are you speeding up or slowing down, right? Like if you're in a car and you like tap on the gas pedal and speed up real slow, maybe you can feel it a little bit. But if you slam the gas pedal, like you can really feel that, or you really feel pushed back in your seat. See, okay, so it's different values of acceleration, something like that, right? Different planets had different gravity fields. Ooh, I bet that's an type of acceleration. In fact, that's this next one. Lowercase g, I'm going to reserve for a special kind of acceleration, just acceleration due to gravity. Yeah, so you drop a ball, falls down, right? Or your car is rolling down the inclines, right? Those were under the influence of a gravitational field. That's why they were accelerating at all. Now, your cars were not accelerating at the full rate of gravity, gravity field, because of course they were on a 5-degree incline, right? But like a slowed down version of that. Okay, right? You guys got that? Right. So be really familiar with these. Of course, we're going to use them over and over, right? But that's what you're looking for, right? Notice what did not make the list is mass. You guys see that? Mass did not make the list. But maybe you can kind of figure out why. Especially if you tested that last week, you changed out the mass of the car and it had no effect on the motion of the car, right? Okay. Yeah, so say like I throw a baseball in the air and I want to figure out where it lands. Well, if I threw a tennis ball next to, the same speed and we're ignoring air drag, same speed, same angle, right? It should land in the same spot, right? Because even though a baseball is more massive than a tennis ball, that's not going to really affect its motion, right? Okay, you guys all right? All right. Of course, simplifying a few things, but you guys get the idea here. All right. Okay, so you guys did this lab. All right, let's do this. You guys did all these graphs except for this one on the bottom right. Let's go over these again. All right, so where to start here? Okay. So mass versus time. Right. You guys remember, like, if I had you guys, suppose this was like a test question, right? And I just gave you guys all those blank sets of axes, right? Would you be able to go through and fill in what the graphs look like? This is basically what we did on Friday, right? And so I could have lots of different masses, cars, but it was like always the same time. It took the same time to reach the bottom, right? That's why that graph looks like that, right? Lots of different masses at the same time. Okay. We got, all right, x versus t. Oh, we just did this one this morning, right? This is my example, right? So that was like a parabola shape, right? Now it's related to this one here. If you say, okay, suspect a parabola, I can do x versus t squared. That should be, what shape is this middle one right here? Yeah, that's right, it's been linearized, right? Hey, ooh, I bet the slope of that tells you something about the acceleration, although it's not the acceleration itself, but all right, it's all right. It's like all right. Yeah, so velocity versus time. Okay, this is another graph that you guys did, right? If you had speed gates for the car rolling different time intervals, right? I think it was the diamonds you guys had. Right, we got, all right, now this one you guys haven't seen yet, but I think you kind of figure this out. So the car would be, yeah, speeding up as it's going down the incline. Okay, so its velocity is increasing at a constant rate, right? But that constant rate, right, the rate change of velocity, that's what acceleration is, right? The rate that the car is speeding up. And that would actually be a constant value, right? Right, so Earth's gravity field is another one of these acceleration values, right? And so around the surface of Earth, yeah, there's actually a constant acceleration. So it doesn't matter how long the car's been rolling, it's always speeding up at the same rate, okay? Right, so its speed is changing just at a constant rate, right? Right, and then, right, although two I haven't done yet, these are kind of the trickiest ones. So speed versus distance, velocity versus distance. I was going to ask you guys. You guys would have said that though, right? Because you guys did that too, right? And then, okay, if that looks like a square root and you square the v versus x, what shape is that going to make? Yeah, we're back to linear, right? Okay. So there you go. Just recap of that. I don't know. Did you guys have notes out? Do you guys have notes out? Because this could be a good exercise too. Is see if you can see a step ahead. I threw in animations over the weekend to kind of look at this, right? So while you guys are getting your notebooks out, say a car drives at constant velocity. This is a pretty simple scenario, right? So you're on 995, just going straight north toward Jacksonville, just constant speedometer reading, constant speed, constant velocity. Okay. All right. So you guys see these three graphs here, right? X versus T, V versus T, A versus T. This is gonna be a common thing in this class. I will give you some scenario. Again, this one's pretty simple, right? You're just doing constant velocity, right? And I'll say, can you draw these three graphs for the scenario? Right? I threw some equations here, but I think probably you guys could figure this out, I think, before you ever stepped foot in this class a couple weeks back, right? Could you guys say x equals v times t? Could that be distance equals speed times time, right? And then if you know any two of those variables, could you solve for the third, right? For example, here, let's do a couple examples. What if you're driving 60 miles an hour and you do that for 1 hour? How far have you gone? 60 miles, right? Miles per hour times hours. The hours cancels in it with miles. What if you do 60 miles an hour for 3 hours? 180 miles, right? Let's try this one down here. Right? Well, if you look at a road sign side of the road, it says, say Jacksonville is 120 miles away, 120 miles away, right? And you're getting there at 60 miles an hour. So you're driving real slow, right? Knowing everybody on the interstate. 120 miles away at 60 miles an hour. How long is it going to take you to get there? 2 hours. You guys can do that, right? You guys could do, also, how about this one? If you go, say, 180 miles, it takes you 3 hours. How fast were you going? 60 miles an hour average, right? And okay, you guys got that? You guys do that. Now, what do these graphs look like? What do these graphs look like? Can you guys draw those graphs? Go ahead, since you guys got your notes up. Okay. Draw those graphs real fast. So I got distance versus time, velocity versus time, acceleration versus time. I think you guys might be able to figure these out. What are those graphs going to look like? So you're just on the interstate, you're just driving towards Jacksonville, just constant velocity, nothing crazy, you're not speeding up, you're not slowing down, but you are progressing towards Jacksonville. Okay? So what does your distance accumulated versus time look like? What does your speedometer reading as a function of time look like? And acceleration has something to do with like speeding up or slowing down, right? So what does that look like every single second? All right. Yeah. Yeah. Okay. I think most of you guys are. Here, give you guys a little more time here. Yeah. Okay, that's it. Okay. Uh, yep. That's what it looks like. Yep, just like that. Okay. Yeah, right there. That one. Okay, yeah, that's it right there. Uh, almost too close. Too close. All right. All right. So a bunch of you guys got these graphs. So this. I think in my animation, I usually start with the middle one and branch out. So I think that's why I did my animation. Okay, guys, you're driving towards Jacksonville. Your speedometer is just pointing at the same number the entire way, right? Okay. So after the first minute, the second minute, however many seconds have passed, right? Just right. Isn't it like 60 miles an hour, 60 miles an hour, 60 miles an hour, 60 miles an hour, 60 miles an hour? Is that just a flat line right there? Boink. That's exactly what that looks like, right? The speedometer is not changing. Constant velocity in a straight line. Constant velocity means constant speed, but also constant direction. So helps too, right? Right, how about I think it did x versus t next, maybe in the animation, right? So okay, so now this you can technically start in any location. I usually start these at the origin now. Right? So at time 0, you're at location 0, although that doesn't strictly have to be true, but right. Now constant velocity, after say like 1 hour, you've gone 60 miles. After another hour, you've picked up another 60 miles. After another hour, you've picked up another 60 miles. So is that going to look like a linear relationship, you guys think? Right? Yeah, boom, there it is. Just like that. Okay, makes sense? Okay. And then now acceleration, this is the rate that you're speeding up or slowing down. But if you're not speeding up or slowing down, it's constant velocity. How much is your acceleration? Yeah, 0. Okay, so that's just, there's a 0 right there. Okay. Okay, that makes sense. All right. Oh, yeah, there's more of this. I forgot about this, right? The different properties of these graphs tell you, these graphs are all related to each other. Like if you know one of these graphs, you can kind of figure out what the other two look like, right? Show of hands, how many guys are in calculus? How many guys are in calculus? Ooh, looks like over half the class. Okay, now if you're not in calculus, don't worry, you'll be all right. But if you're in calculus, there's a calculus connection here. Calculus, well, the first half of calculus is about rates of change, instantaneous rates of change. The second half of calculus is just that backwards. It's like integration, right? And here, guys, the rate change of your location is not like how fast you're going, and the rate change of how fast you're going could be speeding up or slowing down. That's what acceleration is, right? There's a calculus connection here, right? So when you guys do derivatives and integrals, you can go back and forth on these, right? So the physical property is, I could say the slope of position versus time, right? That's the rate that I'm changing my position. That's what velocity is. You see it? Right? So the slope, and the fact that the slope of x versus t is constant means that the coordinate of v versus t is constant. That goes hand in hand, doesn't it? You see it? Constant slope on x versus t, constant coordinate on v versus t. Right? What else we got? Look at there. I could also go back the other way. Like, could you guys look at the area under the v versus t curve? Imagine this is like a 3-hour block. So I'm going to split this into 3 hours. So if you're going 60 miles an hour for 1 hour, you guys see like a tall, skinny rectangle here I'm drawing my cursor, right? 60 miles an hour for 1 hour, the base of 1 hour, right? That could be 60 miles. Well, that would be the area of this rectangle, right? Let's do another one. What if we do 60 miles an hour for 2 hours, 60 miles an hour for 3 hours? You guys see like the area of this rectangle could represent your displacement. I did delta x, like a change in location, like a displacement. Sometimes I'll say x, sometimes I'll throw in delta x. Okay. right? Like that. Right. Also, that works in terms of units. Let's go back and look at why that makes sense in terms of units. If you're ever, because you guys are going to see so many graphs with so many properties like, the slope of this, the area of this, what does that mean? You can always figure out what the slopes of their areas signify by looking at the units, right? So let's look at x versus t. Guys, if you do rise over run to get the slope, rise over run, what units is that? What per what? Meters per second, right? Meters per second, which exactly describes the speed or velocity, isn't it? Right? And how about the one we just did, velocity versus time? And I'm looking at the area under the curve, which in this case is a rectangle. Right? So what if you take the height of the rectangle, which is meters per second, and multiply by the base, which is seconds? Notice I'm multiplying. Guess what is meters per second multiplied by seconds? Just plain meters. Because if you write it out, doesn't the seconds cancel? Just leaves you with meters, right? Right? Which exactly describes the displacement. Displacement or position could be in meters, right? Is that if you write out meters per second multiplied by seconds, the seconds goes away. Right? Do you guys think the same relationship applies from the v down to a? Right? Like the slope of v versus t in this case is zero slope. And a versus t has zero coordinate. You see that? Right? How about going the other way? How about starting at acceleration versus time, and can we somehow say something about velocity versus time? This one's a little trickier, but right. You guys see there's zero area between acceleration versus time in the time axis? Right? There's zero area. What that means is there's going to be zero change in velocity, right? Because if you have an acceleration, you're changing your velocity. Well, if there's no acceleration, you're just not changing. So whatever speed you happen to be going, you're just going that speed. You're just going that velocity. Okay? So there's no change. Okay. Right, you guys good? Makes sense? All right, so we got next. All right. Maybe I should have done this one before. Okay. There's a go there. I know you guys remember laptop day? It was the second day of school. I played you guys a bunch of Polyfield videos. Now, all my other classes I'm going to play with them. If you guys want to go back and see those, they're all on Google Classroom, right? But right. This is one of the ideas he mentioned. This is one of his stories. He said, suppose you're sitting in a car. Let's say you're going constant velocity on I-95, just 60 miles an hour, just constant velocity, just bopping along. Can you feel the speed? Can you know, like if you were wearing a blindfold and your friend's driving the car, you're wearing a blindfold. Can you feel, the car's going 55 miles an hour. The car's going 70 miles an hour. Can you feel how fast? No. Right. But what you can feel is if the car speeds up or slows down, right? Or does what? Yeah, steering wheel goes around a curve, right? Now, for the next few weeks, we're just going to focus on the speeding up, slowing down. That's linear acceleration. So whenever I say acceleration for the next week, I'm really talking about linear acceleration. That's a rate change in velocity. Right? So if you look at your final velocity minus your initial velocity, there's a change in velocity. I say, what time interval did that happen in? A lot of times I'll do delta t for time interval. Right? So if I went from, say, 50 to 60 meters per second, there's a change in 10 meters per second. And if I did that in 2 seconds, say, okay, got a change of 10 meters per second. It took me 2 seconds to do that. Divide that out, 10 over 2, that's 5. And that'd be meters per second per second. It's called meters per second squared. Okay? Be the rate you're changing your velocity. Okay? You could also slow down, right? If your final velocity is less than your initial velocity, would that be a negative acceleration? You'd be slowing down, wouldn't it? Right? Right? You guys okay? Right. Now, this other one where the guys turn the steering wheel going around a curve, here, I'll give you guys the formula for that, but you guys are not going to see that for a while, right? So don't worry about that one so much right now, but that top one, okay? All right? Okay. Guys good? Right now, I think I know what the next slide is. Yeah, it's exactly what I thought it was. Okay. So let's go back to this definition of acceleration. Definition of acceleration. I'm going to do a derivation with you guys. So wait, switch my screen here. Exactly what's coming up here. Okay, so I just told you acceleration is the rate change of velocity over a change in time, right? Which is like, so final velocity minus initial velocity, right? Instead of saying delta t per time interval, I'm just going to do t. Suppose you start at time 0, that could be true, right? Time, right? Initial time is time 0. Can I do that? Okay. Let's rearrange this. Let's make it not look like a fraction. Can I cross multiply the t? Cross multiply the t. A times t is the change in velocity, final velocity minus initial velocity. That could be true, right? Okay. And then I'm gonna do one more little shuffle. So we're gonna maybe add the v naught over and switch both sides while I'm at it. So you can say final velocity is equal to initial velocity plus acceleration times time. Okay. So okay, how about this? The car driving at constant velocity that had 0 acceleration. If you're not accelerating, this goes away, right? Oh, and look at that. Your final velocity is your initial velocity as long as you're not accelerating. Right? What if you start from rest, like you guys did with the car incline lab? Well, in that case, v naught would be 0, right? So that goes away. Okay. Oh, look at that. That's exactly the graph you guys got with the car and incline. I think that was diamonds, was it? Right? The car was speeding up at a constant rate. So if the car's speeding up at a constant rate, and then you say, well, how much time has elapsed? Then you get to how fast it's picked up. If it starts from rest. Huh? Okay, well, yeah, so why is this plus and not a minus? It could go either way. Like if there's a car braking to a stop, you would throw in a minus here, right? Because if you gave the car a push, if you'd given the car a push, then it would already be in motion. And now it would be like further accelerating in that same direction also. So that's why it could be plus in that case, right? Give the car a push. Okay. But true, if you gave the car a push in the negative direction, or if the car is braking to a stop, you would have to be careful that like one or both of these could be negative. Okay, depending on which way. Okay. And now notice there's 3 kinematic formulas I'm trying to build up to. I know we're getting short on time here, right? But we're working towards this. You guys see we kind of drive this middle one right here, right? We took the definition of acceleration, rate change of velocity, right? And then rearranged it with this algebra, boom, boom, and it looks exactly like that. That's what we just did, right? Right. Okay, so now we got this relationship. I didn't say anything about distance yet, right? But we're gonna have to say that for tomorrow probably. All right, so you guys good? Good for today? All right, that'll be a wrap on today. All right, you guys have a good Monday, and I will see you, well, most of you guys on Tuesday, unless you're a 10th grade. You guys have a good day.